He's an assistant professor there and a member of Montreal Institute for Learning Algorithm lab. And she conducts her research in the development and application of machine learning method to cosmology. And prior to that, she was a Flatiron Research Fellow at the Center of Computational Astrophysics, and also CAPAC postdoc fellow in the Stanford University. And Laurence completed her PhD degree at the University of Cambridge, and where she worked on applications of open effective fields, field theory method to formalism of inflation. And of course, she received her bachelor degree and the master's degree from the McGill University. So today she's going to talk about analysis of gravitational lensing data using machine learnings, and let's give her a round of applause.
All right, thank you. It's really a pleasure to be here. So I'm going to talk about machine learning and strong lensing, as you probably guessed from the title. And so what I'm going to be talking about today is based on mostly on those 4 papers here. So I'd like to start by acknowledging my collaborators, Yashar Hezaveh and also Warren Morningstar, who was a PhD student at Stanford when that work was completed. And also Yeringal and Patrick Putsky and Max Welling, who have sort of guided us through various ways in the machine learning aspect of this work. So I'm going to be starting with strong lensing before I dive into machine learning. So strong gravitational lensing is the formation of multiple images of a distant source through because of the deviation of its light rays by the gravity of some intervening structure. So I said that here we're on the Earth, and there's 2 galaxies, one right behind the other one. So as the light rays of the distant galaxy pass near the foreground galaxy, they get deflected, and so they come to us from different angles. And so as a result, here on the Earth, we see multiple images of the same background galaxy. So it's really similar to what happens at the fish in the corner of a fish tank. If you've ever noticed, you can see 2 images of the same background fish. So this is Mr. Mango demonstrating this effect. So you see, as he goes to the corner of the fish tank, you see 2 images of the same background fish. So I had to wait a really long time for this video to work out. So this is really similar to images of lenses that we see in the sky. So, so here we see 2 images of the same background quasar due to the deflection of its light ray by the gravity of the foreground galaxy in orange here. So of course, in the case of gravitational lensing, the deflection of light is due to the gravity of the galaxy as opposed to refraction, like in the case of the fish tank. Here's another example of a strong lens. So here we see that the light of the background galaxy sort of wraps around the foreground galaxy. So this is really common in strong lensing. Lensing usually forms arcs, and that's because of the geometry of the lens, of the matter in the lens. So you can actually simulate something really, well, reproduce something really similar at home with a candle and a wine glass. So if you look at the flame of a candle through the foot of a wine glass, you see that the flame of the candle sort of wraps around the foot of the wine glass like this. So this is really similar to what you can see in the sky when you look at images of strong lenses. And so in this analogy, the flame of the candle is the background galaxy, and the foot of the wine glass is the foreground galaxy that's distorting the image of the background source. Okay, so you can use strong lenses for a lot of things. So the first thing you can do is that you can use strong lensing as a cosmic telescope. So that's because strong lensing magnifies the images of background sources. So you can use it to study very distant galaxies, for example, that would be otherwise below your sensitivity or resolution limits. You can also use strong lensing to study the matter distribution in the lensing galaxy. That's because it's the gravity of that matter that's causing the distortion in the background images. So you can use it to study things like the distribution of dark matter in lensing galaxies. You can also use strong lensing for cosmology by measuring H0. So the way this works is that if there's some time variability in the background source, the different images that you see, they come from light traveling through different paths. and those different paths can have different lengths. So that time variability is going to show up in your image as a time delay between different images in your lens. So if you measure that time delay together with the matter distribution in the lens, you can use that to measure H0. So that's also very interesting. But if you want to do anything with images of strong lenses, you have to be able to extract some information from images like this. So how do you do that? So if you want to do any science basically from images of strong lenses, you have to be able to model simultaneously two things. You have to be able to model the undistorted image of the background source and also what's the mass distribution in the lensing galaxy. So it's a little bit like looking at the image of somebody in a funhouse mirror. It's like asking what's the undistorted image of the person and what's the shape of the mirror. So to see why these two things completely fix a lensing system, we can look at a similar problem. So let's say that you have the image of somebody, an undistorted person, and you also have the shape of a mirror. It's very easy to simulate the image of the distortions. The only thing you have to do is look at oh, shoot. All right. I'm going to have to start this again. All right, sorry about that. So the only thing you have to do is take the shape of the mirror. You calculate the deflection field. You apply it to your image, and voila, you get the distorted image. So the problem is that when you have actual data, you don't know what's the undistorted shape of the person, and you don't know what's the shape of the mirror. So the problem is that you don't know what's the inverse of that simulative function here that allows you to go to those parameters that are interest. So the way that people go around that traditionally is that they take a lot of different combinations of images of person and shapes of mirror, and they produce a lot of simulations until they get a simulation that looks a lot like the data they observe, and then they conclude that they have the right parameter. Yes?
To reproduce, don't you have different combinations of sources and lenses?
Yeah. So there's a lot of degeneracy, so that's why you need to have good priors for the parameters that interest you. So like, in the case of lenses, you could have no mass in the lens and a source that looks like a ring, but that's not very compatible with what we know about the shapes of galaxies. Yes, so indeed. So this way of modeling things like that to produce a lot of simulations is called the maximum likelihood lens modeling, because to compare the data and your simulation, you use a likelihood function that you try to optimize. So usually that step, the maximization of the likelihood function, is the problematic step, because like you can imagine, it requires the production of a lot of simulations, like millions of simulations for every lens that you want to model. And then the likelihood surface that you're trying to optimize is very complex. So it has a lot of local minima. So it's very common for optimizers to get stuck. And so you have to go by hand and then restart it from a different place. So it makes the whole process very difficult. And then on top of that, well, yeah, or you can spend a lot of time, right? So yeah, so it takes a lot of manual effort. And then on top of that, every likelihood evaluation is also really expensive. So the whole process is super computationally expensive and expensive in terms of human resources too. So like, just to give you an idea, it's not unheard of to need 2 million CPU hours for modeling a single lens. So it's very, very expensive. So that means that modeling lenses is very complicated and long, but we only know of about like 500 strong gravitational lenses altogether right now. So it's not such a big deal that it's long. The problem is that with LSST and Euclid and WFIRST, we're expecting to discover about like few 100,000 new strong gravitational lenses. For example, with LSST, it's estimated that we'll find 170,000 new strong lenses. So that's super exciting for all this science we want to do with strong lensing, because we're going to have a lot of statistical power, and with such a large sample of lenses, there's a lot of chances we're going to find rare events, so that's like really exciting. But then the problem is that how are we going to analyze 170,000 new strong gravitational lenses? So if we assume it takes about 3 days to do the simplest possible lens modeling of a lens, it would take a person 1,400 years to finish the analysis of all the LSST lenses. And that's if the person doesn't eat or sleep or have weekends. So, so I mean, clearly we need new analysis methods. So that's sort of what motivated us to look into the use of neural networks. So if we go back to this slide of the little boy in the mirror, the problem that we had is that we didn't know the inverse function of the simulator here. So we thought because neural networks are universal function approximators, we can use them to basically approximate any function we want. So we thought we can just use neural networks to approximate that inverse function here, and then directly go from the observed data to the parameters of interest without the need of doing all those simulations that made the process difficult. So more specifically, we've been looking at convolutional neural networks, which are a flavor of neural networks that are super well adapted to look at visual data. So the way they do that is that they convolve input images with a bunch of filters to produce the output of interest. So the value of those filters are not fixed ahead of time. They're learned through a process that's called training, where you show the neural network a bunch of images for which you know what the answer is. So basically, you try to minimize the difference between the output of the network and the answer that you know. And so you try to basically find the value of those filters that minimize that difference. So those are used a lot in a lot of different applications. So for example, mostly for classification problems. So for example, on Facebook, the thing that tells you who's in your photos is a network like this. Or they've been used a lot for finding rare events in data, like finding strong gravitational lenses. There's a lot of work that's been done on using those to find lenses. So those are called classification problem, like telling you if there's something in an image or not. But what we wanted to do was something slightly different. So we wanted to input directly telescope images of strong lenses into those networks. And then at the output, what we wanted to have is basically the value of parameters that describe the mass distribution in the lens. So we wanted to do a regression problem. So we wanted to have the network output what's the mass of the lensing galaxy, what's its ellipticity, what's its angle, what's its position, so things like that. All right, so we we didn't use real images to do the training because, like I said, there's not a lot of real strong lenses that we know of. So we used simulated data to do the training because simulation of strong lenses is very easy. So we started from real images of galaxies for background galaxies, then we lensed them, then we blurred it with a PSF, then we added noise. So the contrast is not super good here, so there's not a lot of difference. But so we blurred it with PSF. We added Gaussian noise and Poisson shot noise, then zero bias, hot pixels, and a bunch of cosmic rays. And then finally, we added also a lot of random masks that were allowed to partially cover the rings in order to make the network insensitive to artifacts that we might want to mask in the images. So once the network was trained, we tested its performance on 10,000 new simulated images of strong lenses. I'm showing some of them here. So you can see there's a lot of different range of noise levels and signal to noise level, and some with masks, some with very poor lensing configuration where you basically almost have no arcs here. Yes?
I guys have a question. If we go back to the previous slide.
Yes.
Is there a specific catalog of galaxies?
Yeah, so we used images from Galaxy Zoo and Great Tree.
And then for the lenses, was there another catalog?
No, because we didn't. So okay, so that's a really good question actually. So we just basically sampled uniformly from a range of mass and a range of ellipticities, and all possible ellipticities and different angle orientations and things like that. So that's what we did. So it's because there's no light for the lensing galaxy, we can just use any, and we used parameters of an SIE profile. So there was a very simple parametric model for that. So for this specific, yes.
Question, I'm not sure
Yes.
if you asked it, but you said there's no light in the lensing galaxy. Does that pose any problem? Because
Yeah. So, okay, so I didn't prepare slides for that. I think I have slides, but they're somewhere else. I can show them at the end. So when we did the test example, so here you can see there is no light for the lens. And these are actual lenses from the Hubble Space Telescope. So in those, there would be light in the lens. So what we did for that is that we used ICA to separate the light from the lens from the light from the arcs. And the reason why, so that's why we use lenses where there's at least two different bands of observation to allow to use ICA. And I don't know if you guys are familiar with ICA, but it's an independent component analysis. It's not super popular, I think, in astronomy, but it's a really helpful tool that relies on the fact that a mixture of signal it always looks more Gaussian than the two signals separately. So it tries to, if you have two different band observations of like two different frequency observations of the same thing, then you can find, you can rotate your two observations in a new basis where the two signals look maximally like non-Gaussian to separate the two signals. So it's not, it's similar to PCA, but it works on a different assumption. It works on the assumption that your two signals are independent from each other, hence the name independent component analysis. So we were able to use that to do this, so that's why this process is like super automated in this way, yes.
Can you use, so suppose that you have two different images of the same galaxy, different wavelengths.
Yeah.
So if you see a difference in, I think it has to come from the source galaxy. So can you use this to untangle the contribution of the source versus the
Yeah. So yeah, that's exactly the information that's used, because the background galaxies at a different redshift than the foreground lens, they're going to have different wavelength, basically dependency. So that's the information that you use to do this separation. It's just that with ICA, it's like it's very automated, so you don't need to sit there and find the exact. It's not like fitting a profile to your lens by hand and trying to subtract it manually. Yeah. Any other questions? No? Okay. So yeah, so to test the performance of the network, we used 10,000 simulated lenses like this, and also those 9 lenses from the Hubble Space Telescope. And this is what we get. So here what we have is on the y-axis, we have the prediction of the neural network, and on the x-axis, we have the true value. So the bunch of little points are the 10,000 different lenses that we use for simulation, and the bands are the tiny band in the middle that we can almost not see is the 68% inclusion region, and this one is the 95 inclusion region. And the 9 markers are the Hubble Space Telescope data. So what we can see is that with those networks, we have a really good way of estimating lens parameters. But the main point here is that it's 10 million times faster than with traditional methods. So instead of taking 1,400 years to analyze all of the LSST lenses, it would take half an hour on a single GPU. So that's sort of the main gain. But if you're an astrophysicist, probably what you care about a lot is seeing something like this for your recovered parameters. So you're interested in also seeing posterior samples for the parameters that you recover. So basically what that means is that you want to see uncertainties on the parameters that you predict for the lensing parameters. So the question that we had was basically the question is there a way of using neural network to also estimate uncertainties on predicted quantities? So to look at that, we have to think about what are the sources of uncertainties in neural networks. So there's sort of 2 main sources of uncertainties. The first source of uncertainty is called the aleatoric uncertainty. That's the uncertainty that comes from intrinsic corruption in the data. So this is things like noise, blurring of the PSF, so things like this. But the second source of uncertainty is called the epistemic uncertainty. So this comes from the neural network itself. So basically this is things that's like due to insufficient training or the architecture of your network not being flexible enough to capture the complexity of your data. So in order to capture both sources of uncertainty, the first thing that we thought to do is basically instead of having the network predict a point estimate for every parameter, we wanted to have the network estimate a likelihood for that parameter, a full likelihood. But that full likelihood is very complex because it has a freeform and everything. So you can approximate it basically by an analytic distribution and then have the network output the parameters of that distribution. So if you assume that distribution to be a Gaussian, then instead of having, so this is the log of a Gaussian. So instead of having your neural network predict a single point estimate for every parameter of interest, you estimate the parameters of a Gaussian. So that's basically a mu and a sigma. So now, so for every parameter of interest, you now have 2 parameters that represent a Gaussian distribution. It's important to stress, so this is really similar to doing Fisher analysis to estimate your uncertainties. And it's important to stress here that this is still supervised learning, because you still have labels for the value of the parameter that you want. So that would be basically like a label for the mu here. But you don't need to have labels for the values of the sigmas, because the network's going to learn implicitly what's the right value of sigma. So if it learns, so it starts to predict a value of sigma that is too large, it's going to get, and this is basically what you use as a cost function. So it's going to get penalized by this term here, basically the determinant in the cost function. And then if it learns to predict a value of sigma that is too small, it's going to get penalized by this term here. So it basically learns what's the right uncertainty for each parameter implicitly. OK, so that's great. But then the network can make errors on its estimation of those two parameters themselves. So in order to capture that source of uncertainty, we looked into Bayesian neural networks. So, OK, so what this is basically in a regular neural network, the values of the weights. So this is the values of the filters. Yes? Yes? Sorry?
Even your cost function, there's a parameter which is tuned in your output.
No, the network is going to learn, it predicts the value of sigma, right? So when you want to calculate the cost, so for every parameter, you basically have an estimate of a mu and an estimate of a sigma. So let's say that you're only interested in one parameter, you only want the mass of the lensing galaxy. It's going to give you a mean for the mass and a sigma for the mass. You put those two things, and you want to calculate the cost. So you could put those two things here. So you have the sigma that was the output of the network and the mean that was predicted by the network. But you only need one label, this one, in order to predict this whole cost here. So you don't need a label for the value of sigma because of the way you built the cost function as the log of the likelihood.
Is it possible to have correlated?
Yes. Yeah, you can predict the full covariance matrix, basically. We have not done that. We looked at them as marginalized posteriors for individual parameters. So basically, our sigmas were like marginalized uncertainties for the parameters. But yes, you can do that.
So how do you deal with the work? Because if you have the entire matrix and some terms could be negatives, then what do you do about the log in these cases? And because this is how you weight the size, this is how you penalize, right? The entire log. So what do you do in negative terms?
So instead of predicting actually sigma, you're going to predict log sigma. So that's going to help with this. It's going to be better behaved, basically. Any other questions? No? OK. So yes, so to capture the error basically that the network can make, it's in its prediction of mu and sigma, we use Bayesian neural networks. So in a regular neural network, the value of the weights, so for us that's the value of the filters that we use are fixed deterministic values. So every time you put the same image in a network, you're going to get the same answer at the other end. But in a Bayesian neural networks, you replace all those fixed weights by probability distributions that have sort of a free form. So what you do now through training is that you learn what's the shape of those probability distributions. And now at test time, what you want to do is you don't want to marginalize over those. So what you do is that you Monte Carlo over them. So you feed the same example, the same test example multiple times through the network, every time sampling with different samples of those distributions, and then you collect the output. So you're going to build the probability distributions like that. So then you combine the two sources of uncertainties that give you the final uncertainty. So in practice, Bayesian neural networks are actually pretty hard to train once they get very deep. So we can use another approximation that makes it easier called variational inference, where you replace those free-form P distributions by Q distributions that are analytic, and then you only predict the parameters that describe those distributions. So now to do the training, you have to do something like minimizing KL divergence, but I won't get into details. If you're interested, you can come talk to me after. But so yeah, so you can use any distribution as your variational distribution, the Q distribution. But in practice, if you choose a Bernoulli distribution, it makes your life a lot easier. So what a Bernoulli distribution is that it's either 0 with some probability P, or some value W with probability 1 minus P. So here the value of P is fixed. And I'm going to come back in just a couple of slides on how you fix it. But the value, the W is the variational parameter. So that's the thing that you try to learn through training for every weight. So if you've ever done some machine learning, this is exactly what dropout is. So if you don't know what dropout is, it's fine. It's just a method that's super widely implemented in neural networks library, in machine learning libraries. So the advantage of using that is that you can basically use a tool that's already there to capture your uncertainty. So you don't need to do any additional coding. So it just makes it a lot easier. Okay, so this is an example of uncertainties that we can get for a lensing parameter. So basically, this is the 1 sigma prediction for the network on the y-axis against the true values on the x-axis. So we see that the uncertainties that we get make sense. But then more than that, we wanted to know how accurate are these uncertainties. So the measure that we decided to look at to know if those uncertainties are accurate, like when we say 1 sigma, do we actually mean 1 sigma? So we looked at the coverage probabilities for the uncertainties that we were predicting. So what the coverage probability is basically the coverage probability of an interval is the number of times that the true value falls within that interval. So ideally, you want the coverage probability of an interval to be equal to that interval. So for example, for 1 sigma, you'd like the true value to fall within that interval 68% of the time. So we calculated those for our neural network. So here, what I'm showing is that we actually trained many different neural networks with different values, fixed value of the p, the dropout rate that I was talking about before. So every group of 3 columns here is a different neural network that's been trained with a different value of p. So the p in each group of columns is fixed, but it's different between different groups of columns. So what I'm showing here, every column is a different confidence interval. So this is like the dark blue is 68, the lighter blue is 95, and the very light blue is 99% confidence interval. And then on the y-axis, we have the corresponding coverage probability. So the horizontal line are 68%, 95, and 99%. So ideally, you want the column to match the corresponding horizontal line. And so what we see here is that you can use the dropout rate as a hyperparameter that you can tune to calibrate your uncertainties. So yes?
I just want to understand. So what you did is you trained the network using a certain fixed dropout. And are you employing dropout in the inference to get a distribution?
Yes. So you at test time you keep dropout on basically.
And you get the confidence interval from the on top of the drop from randomly dropping out such that you're doing the inference. Is that right? You're inferencing many times and getting a distribution of the inference.
So you get for one example, you get your probability distribution, and then you look is the true value within like 68% of that distribution or not.
How are you constructing the confidence interval?
Yeah, so you repeat that many different examples.
Okay.
So we have a very large data set because we use simulations for building our data set. So in the test examples, we use different examples to build those.
Okay.
No problem. Any other question? Yes?
Usually we would not expect the model to hit exactly the theoretical rate, right? There should be a scatter that's proportional to the standard deviation. So you also take this into account?
I mean, you see that it's not quite perfect, right? Yeah, but so it depends on how many samples you look at. Like if you look at just 100 samples, it's going to be different than if you look at like 1,000 of them. But you see that it doesn't fit perfectly, and it's also average over different lensing parameters. So there's a lot of averaging that goes into that. But yeah, but just that you get a single dropout rate that fits different confidence, like all the 3 of them at the same time is a really good sign. Yes?
How many layers and hyperparameters do you have, and you implemented the dropout in all the layers, or?
Yeah. You implement it because you want to replace every weight by a probability distribution. That's sort of the idea that's behind it. So you want to have dropout before every single layer.
Each time you just drop out one.
So that's the problem. So that's that's a key probability. So 97% is a key probability. So you drop out 3% of the time.
And how many hyperparameters?
So we trained a lot of different networks. So we trained Inception v4, we trained AlexNet, and we trained Overfeed, and we also trained a lot of networks that we built ourselves. So I think Inception v4 is like 5 million parameters. I think it's the more complex. AlexNet is a lot smaller. It's just 8 layers. So it's a lot smaller network. So what we realized is that once you reach a certain complexity, it doesn't matter. Like the accuracy that you can reach doesn't matter. Doesn't change very much if you train appropriately. So it turns out that lensing is actually an easy problem compared to like facial recognition and things like that. Yes.
Are you doing the dropout in convolutional layers or only in the dense layers?
No, in the convolution layers too.
Okay.
Yes. Any other question? No? Okay. That's good. It's super interactive. Okay, so All right. Okay, so just to recap quickly on this method for getting uncertainties. So basically, we place dropout before every weight layer. Then we train with dropout optimizing this cost function, the log likelihood of a Gaussian. And then at test time, we keep dropout on. And then we put the same test example multiple times through the network, each time collecting the output. And then we combine the two sources of uncertainties. And then that produces the final uncertainty. So this is an example of uncertainties that we obtained this way for real data. What I was showing before was simulated data. So this is a source that was observed with ALMA. So what I'm showing here are basically the seven parameters of an SIE plus external shear density parameterized like density map for the lensing galaxy plus the magnification here. So in black, so these are the posterior. Basically the marginalized posterior for those parameters. And in black, I'm showing that posterior estimated with an MCMC. And in red, I'm showing the estimation done with the neural network. So we see that with every case, the two are consistent with each other. And the neural network uncertainties are slightly larger than the ones done with the MCMC, which is to be expected because you also have the uncertainty of the neural network itself that's added on top of the model, the lens modeling itself. So the point here is that this is about 100 million times faster than with the traditional, MCMC modeling. So it took a couple weeks on 256 cores to get the black lines, but it took 1 second on a single GPU to get the red lines. So that's sort of the point here. All right. Any questions about this? Yes.
Do you think that you said there was a diminishing returns if you train a more complicated network, but shouldn't you have the red uncertainties narrowing if you have a more complicated network, which is more?
I mean, that would have, we thought that this was good enough, so we stopped here. Yeah, it really, you can, but with an increasingly complex network, it can also become more difficult to train. So it depends, because with so many parameters, you have, again, a lot of local minima. Usually all the local minima in machine learning, it's not as bad as in physics. They're actually all roughly equally good, but you can sometimes happen to have a much better one than the others. So there's a lot of training issues that can happen. It can become very difficult to train these. You have to worry about a lot of issues like gradient, in backprop, gradient flow, and things like that. So so it can be more difficult to train deeper neural network. So for the main point here, I think, is that for a lot of science that you want to do with strong lensing, this is not the bottleneck of uncertainty. If you want to do backgrounds for science, it doesn't matter that much that you have such a precise model for the lens, as long as you have a model. And so this can be very useful for those kinds of studies. Or if you want it, if it really matters a lot that you get very accurate uncertainties, what you can use this, and then do importance sampling to get exact posterior estimates without the need to run a full MCMC chain. Yes?
I just have a question. So for the red curve, I guess they're not nearly as narrow for some of them, but some of them are still centered roughly at the same, some of them are same, fairly offset. Is there something more about the science that you can learn with, for example, looking at the Y and the Y-axis?
So this one here is always the best constrained, the Einstein radius, because this is very, very easy to constrain from an image. It's basically just measuring the distance between the images. So that's a very easy parameter to constrain. That represents sort of the mass of the lensing galaxy. Other things have more, for example, the ellipticity and the external shear. They have a degeneracy with each other, so they're much harder to constrain very tightly. So that's why the uncertainties are larger.
I guess not just in terms of the uncertainties being wider, but then also the.
Oh yeah, but that's why they're if they're more offset, it makes sense that it would be larger because they're still consistent with each other. And then they're also wider. So this is only 8 samples, right? So if you wanted to have a good idea that these are actually good, represent they're accurate uncertainties, then you'd have to look at more samples too, and then you'd see that that's why they're larger. Uncertainties. But they're also dependent on the specific lens that you have. So the uncertainties are going to be different depending on the lens configuration that you have. Lenses where you have very extended arcs are going to have much tighter constraints because you have you just from the physics of it, you have more constraints. If you have just just 4 localized images or 2 images, it's going to be much less constraining. So you're going to have much larger uncertainties, and that's what we see with the neural network uncertainties too. More questions? No? Okay. All right. Okay. So everything that I talked about so far was for reconstructing the matter distribution in the lensing galaxy. But like I said at the beginning, we're also interested in looking at what's the undistorted image of the background source. So the way that this is done traditionally is by basically using a parameterization for the background source that's pixelized. So basically, you pixelize the image for the background source, and every pixel becomes a parameter. So if you choose a parameterization like that, it actually becomes a linear problem to go from the source to the lens image, to go from here to here. You basically encode all the parameters of the matter distribution in the lensing galaxy in a matrix. That's called the lensing matrix L. You multiply that by your source, and then you get your lens image here. So the advantage of it being linear is that you can write the solution for this analytically. So this is what it looks like. But then, of course, if you have, let's say, an image for the background source that's 100 pixel by 100 pixel, you have 10,000 parameters now. So this is going to be a heavily under-constrained problem. And so to regularize that, you need to put a prior on the pixels of the background source. So if you add that prior in the solution, it's going to come in here. So that's the correlation, that's the covariance matrix, sorry, of the prior for the background source pixels. And if you just apply this to the image that I was showing at the beginning, just before that the lens image I was showing before, this is the background source reconstruction that you get. So as you can see, this is not perfect. There's obviously some problems here. The main problem is that you get a lot of noise that leaks from here to here. That shows in like those correlated stuff here. So that comes from the prior that you impose. That's because if you want to keep everything analytical, you're forced to use a very simplistic prior, like a Gaussian. And what that does is that it basically puts a constraint on the two-point correlation function in the background source. But that's extremely simplistic. It doesn't really capture, everything that we know about what a galaxy should look like. So it's not a very good prior to put on a galaxy. And so that's what leads to that leak of noise in the source reconstruction. So the question that we had is, can we do better with machine learning? So what we did for this is that we looked into recurrent neural networks. So recurrent neural networks are particularly well adapted for treating sequential data, sequential processes like language and things like that. But sequential process that we encounter a lot in astrophysics is the process of optimization. So that's a sequential process because you start from somewhere in parameter space, you take a series of steps, and then hopefully you end up at a point in parameter space that optimizes a function that you're interested in. So the specific model that we looked into is called the Recurrent Inference Machine, or RIM for short. And it's a model that Max Welling and Patrick Bosky came up with in 2017. So what this does more specifically is that it tries to optimize, basically tries to solve, this function for x, this equation for x. So in this, y is a vector that contains the pixel, the noisy observation. So it would be, for example, the noisy pixels of your observed lens. X is the parameters that you're interested in. So these are the pixels of the undistorted source. F is a function that maps the parameters to the observables. So in our case, that would be the lensing matrix. But it could be any nonlinear function in principle. And N is a vector of additive noise. So if your noise model is Gaussian, then it's very easy to write the likelihood of y given x. It's just a Gaussian likelihood like this. And so what the RM does is that it tries to solve this equation recursively for x by basically, it does a recursion. So at every point of the recursion, it inputs its current best estimate for x and the gradient of the likelihood at that point. And then it uses that to produce the next update to their parameters. So that works in a way that's super similar to what gradient descent does. So just quick recap of gradient descent. So gradient descent algorithm is basically a way to optimize any function f recursively. So at every step of the recursion, you start from your best estimate for your parameters. You calculate the gradient of the function you want to optimize. You multiply that by a constant gamma. That gives you your update, and then you keep on going like that. So the neural network does something extremely similar. It inputs the current best estimate for x, the gradient of the function we want to optimize, and then it uses the neural network to basically predict what's the best possible value for the parameter gamma. And then to predict an even better value for gamma, it has a hidden memory state that keeps track of where it's been in parameter space to basically predict an even better value for gamma. So with the gradient descent optimizer, you can optimize any function. With the RM, we want to optimize the likelihood. So the way this works is the RM produces its best estimate for the undistorted image of the background source. You pass that to your physical model to calculate the lens image. And then you pass that to your likelihood function. You take the derivative with respect to, but the gradient with respect to the parameters. So these are the pixels of this image here. And then you pass this back to the RM, which produces the next update. So you do that, you keep on going like this until the process converges. And then during training, what you do is that at the end of this whole recursion, you show the true image to the neural network. And that's what's going to allow it to learn where it should have ended up in parameter space. Yes? So with gradient descent, first of all, your gamma is fixed for all your different parameters. So this can decide, so if I have like 10,000 parameters here, it can decide what's the best update for every single one of them individually. Any other question? All right, and I'm going to show in a little bit like something else too, that this is learning on top of that. So, and then once the network is trained, you can test its performance on new images. So this is the image that I showed at the beginning. So the contrast, I think, is not very good here, but like there's actually more information here. So yeah, so this is the observed image. This is the ground truth. This is what the RM reconstruction recovers, and this is the linear inversion that I showed at the beginning. So this is basically the state-of-the-art method that you'd have before the machine learning paper that we published. So yeah, this may be a little bit better. So just clearly by eye, you can see that the RM is doing better. But just to quantify how much better, we looked at the coherence spectrum. So that's basically the cross correlation between the reconstruction and the true image. So that's what I'm showing here as a function of scale. And the closer this is to 1, the better the reconstruction is, basically. So in blue, I'm showing the RM reconstruction, and in red, I'm showing the linear inversion reconstruction. So we can see that on every scale, the RM is doing better than traditional state-of-the-art method. So just to see how I'm doing with time. All right. So yeah, so this is really interesting because first of all, just up to now, we were mostly using machine learning to speed up the analysis process. But this is like a first example where machine learning can actually do better than traditional methods on top of it being a lot faster. So this is very interesting for this reason. And then just to give a little bit of insight on why the machine learning method manages to outperform traditional state-of-the-art method, it's because, like I was mentioning before, the linear inversion is constrained to use a prior that's extremely simplistic for the background source. But in the neural network, you don't have to write down that prior. So the neural network is free to learn this prior implicitly from the training data. So it can learn a much more complex prior function that's much more representative of what a galaxy should look like from its training data. So that's where machine learning can improve a lot on traditional methods. Yes?
If you really wanted to go fast with a good estimate, you would also want Gravitational. You try and put that in the system.
Yeah, so we haven't needed to do that. For us, this was really, so it was actually very efficient at optimizing the likelihood and the way it currently was. And it wasn't even getting stuck in local minima or anything. So we didn't really need to add momenta to the optimizer, basically. Maybe there's some cases where, because this is still a simple problem because it's a linear inversion. Maybe in some cases where the physical model is nonlinear, that would be a very good thing to try. Yes.
Well, what I'm interested in here is the statement, which I think is correct, is that if you do a little pre-processing of any Bayesian network and a Bayesian flow, however you want to word it, try to use machine learning, you can speed it up enormously. So that's the answer that you're telling us here, which I think is correct. But there are traditional methods that one uses in order to try and do convergence quickly.
Yeah, that would be very interesting, yeah.
One's using, as I said, the second gradient. And usually what happens in those cases is often what happens is that you actually can't calculate the likelihood. I mean, calculate the likelihood. It's hard to get the derivative and the second derivative except for numerical methods, finite differences.
So with this, the advantage of this is that we can use AutoGrad for this because everything's implemented. So because the modeling is implemented in a way that the derivatives we can append the derivatives with AutoGrad. So we don't need to calculate the derivatives numerically. It's the same way that backprop is calculated, basically.
And the lens is being updated along with the image. Everything's updated. So
Yeah.
Your final result.
Yeah.
It's the lens model that's most consistent with the source model. It looks like.
So we did that actually. When we were doing the training, we were always using the true lens model because we were working with simulations. But at test time, we tested not having the correct lens model. So we were estimating the lens model with the other neural network that I presented at the beginning. So that was just an approximate lens model, basically, at every side of the recursion, yes. Okay. So, all right. So this is just a fun example because a lot of people criticize neural network for being really bad in extrapolation mode. So we thought we should test the robustness of the results that we get on an example that's really far outside of the training data. So what we use for the background source is some text here. And so we lensed the text and we added noise and everything and all observational effects. And then we inverted it with linear inversion methods and with the RM. So we see that first of all, the great thing is that it didn't break the RM, which was great. But it's really good because it shows some robustness basically on what it's learned about lensing and the properties of the likelihood it's trying to optimize. And yeah, you can read the D, but then the PSF gets really bad, really outside of the the very central place. Whereas here you have much better, like it's a little bit more blurry here, but overall you get a better image reconstruction, and you don't get all that noise leakage here. It's the same thing. Like here, same thing as before in the other image I was showing. You don't get as much noise leakage here because it learns a correct pattern that you should have no flux close to the edges. All right. Okay, so everything that I talked about so far was for optical data. I think there's not a lot of time left, so maybe I should just skip this. But we also trained the same model to analyze interferometric data. So we basically trained this to clean interferometric data and then apply the convolutional network that we trained before. So I'm not going to talk about this. All right, so everything that I've talked about so far was for cases of galaxy-galaxy lensing, where the lensing galaxy is extremely simple. So you can basically parameterize its mass distribution with like 5 or 7 parameters, something pretty simple, like mass, angle, ellipticity angle, and position, and external shear. But in a lot of actual examples of strong lenses, things are a lot more complicated. Like for example, here there's 2 galaxies in the lens. So clearly we need to have a parameterization for the mass distribution in the lens that's more flexible. So one thing that we can do is that we can use a pixelated map of the projected density in 2 dimensions. And so to do that modeling, what we're doing right now is that we're trying to use 2 RM networks that work in parallel with each other. So basically the first network is this one that I just talked about that reconstructs the undistorted image of the background source. And the second RM, its job is to reconstruct the density map, basically the projected density map in the lensing galaxy. So they work together because they share the same forward model and they share the same likelihood. And you try to optimize it jointly between the two sets of parameters. So to train this, we're trying to use more complex density maps. So we're using galaxies from the Illustrious simulation, which are very realistic galaxies. But what we realized is that there's actually not that many galaxies in the Illustrious simulation that are massive enough to cause strong lensing. So what we've been doing is that we trained Variational Encoder to produce more examples of galaxies that are also realistic looking. So autoencoder is something pretty interesting. It's basically a neural network that learns the identity function. So what it does is that it starts from an image, and then it tries to compress it down to fewer parameters, what's called the code, and then it decompresses it back to exactly the same thing. So if you have a good autoencoder, it's just an identity function. But the reason why it's useful is that once you have one that's trained, you can basically sample your code at different places for different numbers, and then just decode those numbers, and then you get new realizations of what you started with, like example of things that you started with that you didn't have in your training examples. So you can use that to generate new examples of galaxies. So these are some galaxies that we've generated with the variational autoencoder. So you can see that they're pretty realistic looking galaxies with a lot of interesting structures. And then we can train the double RIM that I was talking about before. So this is extremely preliminary results. We haven't put a lot of effort into fine tuning the training, but it's just to show that we can get pretty amazing results just from that. So this is the observed image. This is the model that we get. This is the true background source. This is the reconstructed background source. And here, this is the pixelated density map here, and this is the reconstruction from the neural network. So you can see that it's a much more complex structure here. Even if there's room for improvement, it's very asymmetric, and there's like very extended structure here. So this is something that we would never be able to do to model with traditional lens modeling methods. So this is way beyond what we would be able to do with traditional methods. So that's super encouraging for the future of this research. So another thing that I want to mention quickly is that basically, so what we also did something different. We were interested in knowing if the neural network is learning something fundamental about lensing, or if it's just basically a dictionary lookup. So is it just spitting out the answer from the closest training example, or is it actually learning something about lensing, which is what we want? So what we did is that we trained one of those neural networks on images like this, where there's always only 2 galaxies in the lens. So it basically learns to reconstruct this. So this is the input, and this is the output that we want. So we see that it learns that there's 2 galaxies in the lens, and it works pretty well. But then we thought, what about if we showed it an image where there's 3 galaxies in the lens without any further training? So it's only seen examples where there's 2 galaxies in the lens, and now we give it an image like this that's basically, you just see the lens image, and it's been done by 3 galaxies. But the thing that's important to stress here is that the different configurations that you get from having 2 galaxies in the lens and 3 galaxies in the lens is super nonlinear. So it's not something that's very easy to infer if you've never seen a galaxy with like an image with 3 galaxies in the lens. Sorry, but we were really surprised to realize that in many cases it was able to tell that there were 3 galaxies in the lens, like all of these. And so this was really encouraging to us. It was really telling us that instead of it just being a dictionary lookup, it's actually learning that correlation between the brightness of different pixels in the lens image is related to overdensity in the lensing galaxy. So that's really the thing that it's learning. So this is very encouraging. So this is sort of the first step. This is really just the first step for, yes?
So training sets were all pairs.
Yeah.
So then when you run a new image on it, it's trying to do pairwise reconstruction, but it can do lots of pairs. And so one thing can connect to others. So there must be something that you're imposing that stops the process of pairs so that it doesn't. I mean, in principle, you could have done that thing by lots of little pairs along it just to try and reconstruct it. So there must have been something that's restricted the ability to try and build that complexity that's going down in the information chain.
Yeah, so what I think is I mean, I don't think I have a definitive answer on this because it's pretty difficult to like open the box and look at exactly what's happening. But I think it's really along the lines of what I was talking about before, that through your training set, you're sort of imposing a prior on what should be there. So it's really going to spit out 3 galaxies when there's really actual evidence for there being 3 galaxies. Like it couldn't do the same with just 2. Because it's sort of learned a very strong prior on there should only be 2 galaxies in images.
The galaxies nearly equivalent, because you could also imagine having a pair in which one is really tiny.
Yeah, exactly.
Which is large, in which case it could.
Yeah. So I mean, I'm not claiming that it did it like okay. Just disclaimer: I'm not advertising doing science in the mode with machine learning in the mode of extrapolation. That's not a good idea. You should not do science in extrapolation mode. It's just an interesting thing to test what the neural network is learning to try to probe the modes in which it's going to break. So there are a lot of cases where the network did not manage to recover that there were 3 galaxies in the lens. But just that in some cases it managed to do it is interesting. Like for example, you could imagine that you have a configuration where you had two galaxies very close to each other, just like in front of the background source, and then there was a third galaxy that was really far out, in the corner of the image, and that would not manage to do, because the prior that it's learned is that there, unless there's really strong evidence for it, there shouldn't be like a galaxy in the corner. Does that make sense?
Do you have a theory of fluctuations? Presumably one can with neural networks, so that you could then say what is the true prediction, if you like. There would be fluctuations around it.
So one thing that I have not done here is that there's no uncertainties in those maps. So one thing that I really want to implement like further down the road in the soon future is to be able to have samples of the posterior, basically, to be able to produce. So if there was multimodality and it could be 2 galaxies or 3 galaxies, and this is sort of a disconnect, so you'd be able to sample that and know what's the evidence for what's versus what. So like I was saying, this is really just a first step to show if this is promising or not. But in the longer term, what we would like to be able to do is to be able to model systems that have traditionally be extremely difficult to model. So things like, even very simple looking lenses like the horseshoe lens here that I was showing at the beginning, it looks like it's super simple. There's only one galaxy in the lens, there's one background source, but we have not been able to model that lens with traditional methods so far. So there does not exist a good lens model for this lens. Or more complex systems like this, or in smaller scales, the problem of finding substructure, dark matter substructure in the halos of lensing galaxies has been extremely difficult. So this is a method that we could imagine could really help a lot along those lines. Or on much bigger scales, in the scales of cluster lensing, this has also traditionally been an extremely difficult problem to do with with traditional methods. So we hope that machine learning could help along those lines. So I think I don't have any more time, so I'm just going to stop here.
Some questions?
I may have missed this, Neil, when you said it. If you go back to the, what's it called? The variational autoencoders.
Yes.
So when you're doing that to generate effectively models.
Sorry.
Was there any separation between, say, the morphology of the galaxies that went in? Like, did you do separation of the encoder end with galaxy morphology? Or did you just like literally throw everything in on the encoder end, and at the decoder end it spit out this variation in morphology that still looks like real galaxies?
So there's many different things you can do. You can have a conditioned variational autoencoder. So for example, galaxies look very different depending on their mass. So less massive galaxies, they tend to have like a lot more, like gas structure and things, whereas like very massives are just like those big ellipticals that don't look like much. And so if you can pass an additional parameter that's called the condition to it. So you basically condition your code here on that parameter, and then the output is only going to be one of that like class. So if you have like a mass as your parameter that you condition on, then you can produce galaxies only of a certain mass, for example. But you'd have to have that tag on your training examples. Yes?
Do you have some examples where the algorithm is bad?
I mean, during training, at the beginning, it's really bad. I mean, I didn't prepare bad examples. I mean, like, but it's so the thing here is that it's really important to stress that when you're actually doing like science, scientific results, you really want to ensure that you understand your data really well. So you want to make sure that you're in a regime of interpolation inside your training data. You're not in a regime of extrapolation. So that's like a way of ensuring that you have good performance.
Do you always know? I mean, if you're faced with the horseshoe.
Yeah. So with the uncertainties, what we realize is like with the neural network that predicts uncertainty, we realize that, for example, when we're in a signal-to-noise regime that's larger, the noise is larger than what we trained on, so the signal-to-noise is smaller, then the uncertainty starts becoming much larger. So it sort of detects that it's in an extrapolation regime in this way. So that's sort of a way of telling. Yes?
So you mentioned that you only get marginalized errors, and one thing I heard was classification tasks with deep learning is you can do classification and regression. So if your parameters are not so many,
Uh-huh.
and divide it into bins and predict on which bin it is,
Mhm.
and then have a second network predict which sub-bin of that other bin. But
Mhm.
the sub-bin is for all bins.
Yeah.
And then you sort of have large, you have joins.
Yes.
So I
Yes.
wonder if you look at that for this.
So we did not need to look at that for the lens modeling part when we were modeling the lens parameters, because the accuracy that we were getting was already not in the case of the interferometric data, because there's multiple things that fold into this, but in just the Hubble data case, for example, we were already the accuracy we were getting was already comparable to the one that you get when you use just regular maximum likelihood lens modeling. So we knew that it was a simple enough problem that we were already getting pretty much as good as you could expect to get. But yeah, so that's something you could look into if it was a much more difficult problem. But for the case of lensing, I would suspect that there would be a lot of overlapping, like what you would learn in your first couple, like most of the layers of the network in the classification and the regression network, it would mostly be the same thing. So there would be a lot of overlap of information. It wouldn't be so useful to do something like this, I think. That's my gut feeling.
Any other questions? Well, if there's no other questions, let's thank you.